Okay. Please help me welcome our guest speaker for the morning, Dr. John O'Mara, Chief Scientist at the W.M. Keck Observatory. Dr. O'Mara earned his PhD in physics from UC San Diego in 2000. Is that correct? In 2000, an observer at Keck for 20 years. He joined the observatory in 2018, where he now serves as the primary scientific liaison with the organization's scientific stakeholders, while also playing a central role, excuse me, in setting its science policy. Dr. O'Mara has 90 or more refereed publications to his credit and has been named principal investigator for a series of large funded research grants. His research interests include Big Bang nucleosynthesis and the formation and evolution of galaxies. He is actively involved with a number of organizations that are considering the future of ground and space-based intelligence. At this point, let me give a shout out to Maureen Salmi. Maureen is a docent both at Keck and at Palomar. She has been with the docent organization here since 2011. Hi, Maureen, wherever you are. There you are.
Oh, hi, Steve. Thank you. Wow, it's been 10 years.
Well, my, how time flies.
Yes.
Okay, we'll take questions at the end. You can type questions into the chat, and we'll try to get to them during the question period. And again, I'll ask everyone to mute their microphones. And with that, Dr. O'Mara, thank you for joining us. And please, the floor is yours.
Well, thank you very much, Stephen. It's really great to be here with all of you virtually. Good morning from lovely Kauai, Hawaii. Normally I live on the Big Island, but we happen to be vacationing this week. So I'm on Kauai, missing some valuable hot tub time, but it's actually much more fun to talk about this stuff than hot tub time. I suspect, given the conversation at the beginning, that some of the introductory material will be a bit introductory, but it helps even the playing field so that we're on a common ground to start. But I'm going to go ahead and share my screen, and we'll go ahead and get started. Hopefully, Stephen, this can be seen correctly.
I am seeing it correctly. Yes, I'm seeing your introductory slide.
Great. And just I'll continue Stephen's request. If everybody could go ahead and mute, that would be great. All right. So before I get started with any of this, I do want to wish a happy birthday. In fact, it was on this day, 31 years ago, aboard the Space Shuttle Discovery, that the Hubble Space Telescope launched. If you haven't seen it, every year the Space Telescope Science Institute puts out the anniversary image. This year's anniversary image is just as beautiful as many of the other ones. And so happy birthday to Hubble. It's a little bit smaller than Palomar and a little bit smaller than Keck, but we still love it so. All right. With Hubble in mind, I want to start off with giving you an image of nothing. And this image of nothing was something that the Hubble Space Telescope decided to do a few years after the mission started and a few years after the optics were corrected, in which the director of the Space Telescope and Science Institute at the time decided to take a radical step and take an image of nothing. They picked a spot on the sky where they thought there was nothing. They turned on Hubble, let it run for about 1 million seconds, and they got this. And this is one of the most iconic and famous images of all time, the Hubble Deep Field. And this was truly profound and exciting, but I would also argue that it's only half of the story, because this is a lovely image. It's a breathtaking image. There's about 10,000 galaxies in this image. If you want a figure of merit and ask yourself, how big is this on the sky? What I suggest you do is take out a dime, hold it at arm's length, and look at Roosevelt's eye. And that's about how big on the sky this image is. And there's about 10,000 galaxies in there. But this image lacks something. For all of its beauty, for all of its importance, for all of the critical things that it has done, it lacks something, and that something is context. And I want to tell you the story of the context here, because you can look at a beautiful image like this and you can ask, so what? You know, what is that dot? Or that one? Or that one? There are tiny, tiny little dots in here that you probably can't see on your screen. And you can ask the question, you should ask the question, is that a very small galaxy? Is that a galaxy that's very far away? Is that an individual star? Is it just a clump of fluff? We don't know what these things are. And this image alone cannot tell you that story. So what I want to do is tell you a brief history of a bunch of squiggly lines, which is my way of describing spectroscopy. And this is not necessarily a new thing. We've been doing this for a very long time. We've been spectroscopists for a very, very long time. Here is a beautiful image of Mauna Kea in the background with a nice bit of snow on top of it. And Hawaii, the state of rainbows. You know, you can get a rainbow pretty much every day, multiple times a day in Hawaii. But of course, you know, we now know the deeper mystery behind these things, but we've basically been doing spectroscopy on the sky ever since we could look up at the sky and see rainbows. And why is that important? Well, the first real systematic exploration of what was going on didn't start until much later, after even the invention of the prisms. Romans, even pre-Roman times, there were prisms out there and people using crude optics to play around with light. But the real systematic exploration started to happen in around the 1600s. And it culminated in a really important work, which was this one. This is Newton's Optics, written in 1704. And in his treatise, Newton put forward the pretty profound concept that white light was actually made of a combination of colors. And this went counter to Aristotelian times, which said that light had merged with darkness and properties of materials to make colors. And although we view Newton as a true genius and insight now, this work was extremely controversial and really not adopted in beyond England for quite some time. In fact, Newton held off publishing this because he had a feud of sorts with a physicist named Hooke. And so he waited for Hooke to die before he could publish this, to not have somebody arguing with him. And while Newton was right about the nature of light, or at least in a crude sense, what his treatise on optics, which used a very complicated system of prisms and lenses to really play around with light and look at its constituents, it still couldn't do one of the other things that people knew, which was explain the sets of colors that happen when you throw certain materials on a fire, right? The optics, he could help explain some of the nature of light, and Newton at the time believed in what he called the corpuscular theory, that light was made of a bunch of tiny particles. But he still couldn't explain this, which was known since the ancient times, which is if you take certain salts and you throw it on a flame, they shine particular colors. And so it's the story of figuring that out, which will tie back into that image of nothing. Now, Newton is a very well-known name, and this guy is not so well known, but is absolutely fantastic, and I suggest you look him up. It's a man named Wollaston. And Wollaston has a prism named after him. And in fact, I think there's a Wollaston prism in one of the instruments at Palomar. But Wollaston is arguably a scientist who should have written more down and been louder about it. It's possible that Wollaston discovered the inductive theory of electromagnetism before Faraday did, even though we call it Faraday induction right now. He discovered a number of elements. And he basically made the first lens that was figured correctly to go into a camera. So, people had been playing with lenses for quite some time, but he created a lens system specifically designed for cameras. And important to this discussion, Wollaston upgraded Newton's systems of lenses and prisms, in particular so that he could start to look at what he called gaps in the spectrum of the sun. He would magnify to the best extent that he could the spectrum of the sun, and he saw that there were gaps in them. Now, you could think that Wollaston is really awesome, and he is, but he was also kind of an interesting person because he really hated the metric system. He apparently spent quite a long time in his career rallying against the metric system, and he helped establish the gallon. So, there's a couple of things that maybe perhaps we can get rid of and just all have the metric system. But, Wollaston was a really, really interesting guy. But his gaps are really what's part of the story next, because that leads to this guy, whose name is a little bit more well-known, especially in terms of those gaps. This is Fraunhofer. And Fraunhofer did something really, really important. He took Wollaston's set of optics and upgraded a key element. He took the prism and replaced it with something we call a grating, which is just a thin piece of glass with a bunch of prisms notched into it, but they're very, very, very small. And they act as effectively as a prism. But the advantage to a grating is that there are huge gains in what we call resolution, the ability to see finer and finer details as a function of wavelength. And because he could have this much, much higher resolution and a much more accurate scale of wavelengths, this was a really big deal in the studying of the gaps and in the studying of the nature of light, right? And so these are the gaps were renamed later on to be called the Fraunhofer Lines. And what's shown here is just effectively a drawing of the sun's spectrum with all these gaps in them. And so by having the grating there, one could see not just one or two lines smudged together, but hundreds, if not thousands, in the spectrum of the sun. And this really caused quite a stir, trying to understand what was going on with the sun. That brings us to this rather tired-looking individual. This is Foucault of pendulum fame. But Foucault and later on Bunsen and this guy, Kirchhoff, created basically a new field, which was called spectrochemical analysis. They took Fraunhofer's system and Wollaston's system and the systems of others, and instead of looking at sunlight, they started to look at specific elements, going back to this idea of throwing salts on a flame and you get special colors. So what they did in this spectrochemical analysis is to take specific elements, heat them up, or look at light as it passes through a set of gas and see what happens. And this is an example from an element that they didn't play around with as much early on, but then later became quite famous, right? Which is the spectrum of hydrogen, the most abundant element in the universe. And what they noticed was something absolutely intriguing, which is that if I heat up a bunch of hydrogen gas and pass it through this optic system, I see these bright emission lines. And if I pass white light through cool hydrogen gas, I see these dark notches in it. The white light makes the smooth rainbow, and I see these dark notches in it. We call these an emission and an absorption spectrum. And the critical thing here is that those lines are in the exact same spot in wavelength. And there's also a relationship between wavelength and energy, but critically, those two things are in the exact same spots in wavelength. And this led Kirchhoff to create what they call Kirchhoff's laws, which aren't laws, they are just observations of the universe, but we call them Kirchhoff's laws because okay. And Kirchhoff summarized all of this in the following way. If I take a hot light source, like an incandescent bulb, a very, very hot piece of metal, pass it through a prism, I see a smooth distribution of light, the rainbow of colors. On the other hand, if I pass that same light source through a cloud of cooler gas, pass that through a prism, I see those absorption lines. Or if I pass the light from the gas itself, not from the light source, but from the gas itself, and pass it through a prism, I see an emission line spectrum with the lines at the exact same wavelengths. So Kirchhoff's and Bunsen and Foucault's system of coming up with spectrochemical analysis directly linked what we were seeing in these emission and absorption spectra with the elements. And that really started the races off in terms of trying to explain what was going on. And now we're getting somewhere. So there is some sort of link between these lines that we see in the spectrum and the nature of the elements themselves. And shown here are two gentlemen of names you might recognize, Balmer and Rydberg, who decided to try to explain that hydrogen spectrum, but they now did so instead of elements or anything like that. They wrote down an equation. They predicted the location of these lines as a function of wavelength. They said, all right, if I've got it right, I'm going to guess that at 653 nanometers, I'm going to see a red line. And at about 487 nanometers, I'm going to see a greenish line and these things. They wrote down an equation which very accurately predicted the location of the emission or absorption lines in helium, or excuse me, in hydrogen. Now, this is fantastic and it's amazing because it has predictive power. It allows you to predict where the next line in hydrogen might be, but it's still missing that last piece. And that last piece is the why behind the equation. Writing down an equation to predict things is very powerful. It's a very useful utility, but it doesn't tell you much about the universe. And it doesn't allow you to go beyond in your predictive power until you get to these three gentlemen, right? On the left is Max Planck. On the right is Niels Bohr. And in the center, having a much better time, apparently, than Planck or Bohr, is Albert Einstein, who all together, roughly at about the same time, created the basic fundamental principles of what we now call quantum mechanics. And quantum mechanics, along with many other people not shown on this diagram, provided the why. It provided the actual prediction behind the equation as to why those lines were appearing in those spots and why every element had its own characteristic set of lines. Now I'm going to over-trivialize quantum mechanics and show it here in what Niels Bohr's version of the atom was, which we now know to be an approximation of truth, but nowhere near it. And the basic description in quantum mechanics is that the electrons orbit around the nucleus in specific energies. So unlike the Earth orbiting the sun, or Mars orbiting the sun, or Jupiter orbiting the sun, electrons orbit around their nucleus in very, very specific orbits. And each one of those orbits have a very specific energy. And their electrons are only allowed to be in those orbits. They're not allowed to be in between. And what happens in quantum mechanics is that if you want to go up an orbit, you need to get energy to do it. You need to have energy added to the process and kick it up into a higher orbit. It's kind of like to get to Mars, you need to have the rocket thrust. If you fall down in orbit, on the other hand, you can give off energy. And this was the natural explanation for those lines. The emission lines are what you see when electrons fall down because they have to give off energy. They have to give off an energy exactly equal to the difference in energy that you need to stay in those orbits. And those are the emission lines. On the other hand, if you want to go up in orbit, right, you need to take energy away, which is you need to absorb that light of that exact energy to be kicked up. And this was the physics description of the emission and absorption lines in the spectrum of hydrogen. And this fundamentally transformed our understanding of the universe. Because if you look very carefully now at these lines, you have the rules of quantum mechanics, which tells you where the line should be and exactly what their energies are. And if you know their energies, you know their wavelengths. And if you look very closely at these lines are not infinitely thin. They have a shape to them. And thanks to that fellow Planck on the left, understanding this shape means you can actually understand the exact temperature of the gas that's making those lines. So not only do you have a description of why they have the energies they are, but you have a description of the environment that they live in. You now understand the temperature of that gas. And moreover, if you take that gas and you move it relative to where your prism is, you can actually see differences in the position of those lines. And this is due to the Doppler effect, right? Just like if you stand next to the train tracks, please stand next to, not on. And you listen to the train go by, you hear its pitch go meow. You've all probably talked about this many times in some of the previous talks. But because the source is the source that's making the light is moving relative to you, you either get a compression or stretching out in the case of sound, due to that relative motion. And so objects which are going away from us have their lines all systematically shifted to the red, and objects which are coming close to us are all systematically shifted to the blue. So think about what this means. Now with a single spectrum, armed with the power of quantum mechanics to predict where the lines should be, I not only know what the stuff is made out of, I know what its temperature is, and I know how it's moving relative to us. And this is probably one of the most fundamental things and one of the most fundamentally important things for astronomy since Galileo pointed up at the sky in 1609. Because now we can take the spectrum and understand it. This is the spectrum of the sun. Please do not look at the sun. But the spectrum of the sun having now thousands of lines, this is a very high resolution spectrograph, taking two of those gratings that Fraunhofer and others created to come up with this spectrum of the sun. And the blue wavelengths are at the top, the red wavelengths are at the bottom. And if you were to plot out the intensity of this light as a function of wavelength, that's what you get here. So this is the spectrum of the sun, hundreds of thousands of lines in it. But powered by quantum mechanics, you can now tell what's in the atmosphere of the sun without ever visiting the sun, right? Trust me, you do not want to do this experiment in situ. You would much rather be able to understand the atmosphere of the sun this way. And these are those absorption lines that Kirchhoff described in his laws. The inside of the sun is extremely hot. The atmosphere surrounding it is cooler. And so we see absorption due to the elements in the sun. There's some very pronounced features here, like the sodium D lines. For those of you living in California, particularly in areas near observatories, there are these ugly brown street lamps. That's high pressure sodium. And they do that so that you can subtract a very simple spectrum off if you're trying to do astronomy nearby. If you live in San Jose, you see the spotlights that way too. But there's a number of elements here. And in fact, this was one of the ways that we discovered helium, which was actually in the spectrum of the sun. And it's named Helios because the sun's named Helios. So why is this important? And how does this transform astronomy for the next 120 years? Well, the field of astrophysics is now born. Prior to this, we were doing basically astronomy, finding things on the sky, cataloging them, writing them down. But what we were not doing is explaining how they were. We needed spectroscopy to do this. So I'm going to give you a truly profound theorem by an extremely profound philosopher, me, which says the laws of physics are the same anywhere and anywhen in the universe. I did not actually come up with this theorem. This theorem is the cornerstone, for example, of Einstein's theory of general relativity, that the laws of physics are the same everywhere for all observers. But if we think about what this means for astronomy, that means all I need to do is to understand atoms here in the laboratory, to understand how they're working in stars, how they're working in galaxies, how they're working at cosmological distance between us and sources which are 10 billion light years or more distant. Because we understand quantum mechanics and because we can do experiments in the lab to understand where those lines should be in the spectrum, we can now understand the physics of objects we will never visit, we will never touch, we'll never get anywhere near them. In many cases, objects which are long since gone from eternity. But because we have this theorem, this belief that atomic physics is true everywhere in the universe, spectroscopy allows us to understand the universe. And so I'm going to take that fact and give you a select number of fun results from the last few years in no particular order because I love all my astrophysics equally. And the first is an extremely trifling question. Where the heck did the elements come from in the first place? Right? This group certainly knows that, Carl Sagan likes to epitomize it as us being made of star stuff, a way for the universe to know itself. But this is common knowledge only really since the 1950s. There was the hypothesis that stars are powered by fusion. This is the process by which here protons are joined together to make helium nuclei, and they release off gamma rays, and in doing so provide the pressure that's needed to keep the sun from collapsing upon itself. But you're taking hydrogen and turning it into helium. And later on in the lifetime of that star, helium can combine with more helium to create carbon, add some more helium, and that's the oxygen you're breathing right now. Now, this was supposed in stars, but again, you can't do the experiment directly. I really do recommend you try to go to the core of the sun and try to make this measurement. But because we were learning how nuclear physics worked in the 1950s, and because we understand spectroscopy, there's a way to prove that this is happening in the sun. And that way to prove it actually happened in part of Palomar, which is the observation of a set of stars with a 200-inch. And they've observed an element called technetium. Now, this is not an element that you're used to in everyday life, but technetium is really important for the following reason. Technetium has an extremely short lifetime. Why is that important? Well, if you look at something like the sun and you see the element technetium in it, and if you want to know where it is, it's right there at around 4,262 angstroms. That little dip right next to niobium and gadolinium. But that technetium line, because it's so short-lived in the lab, means it had to be produced in the star. Otherwise, if it was sitting there in the lab, it would decay and it would go away. So there was continuous production of this element in the star. And because we had predicted with nuclear physics how to produce technetium, this was slam dunk proof that the nuclear process, the nuclear furnaces, are what's driving stars. And so this is one of the most important discoveries in all of spectroscopy, the absolute proof that nucleosynthesis happens in stars. That's how stars are powered. And with that, many other papers like Burbage, Fowler, and Hoyle, also known as B²FH, described the creation of almost all the elements that we see in the periodic table in everyday life in processes inside the cores of stars. Okay, let's look at another just minor issue. How about the history of the universe, right? Cosmology is a royal pain to do in practice because the universe evolves over very, very, very long time scales, even longer than, the amount of time I'm willing to make a graduate student work on a thesis or things like that. And so one asks, is it possible to even comprehend the totality of the history of the universe? Folks like Einstein and going back, thousands of years believed in a static eternal universe. But with the increasing power of telescopes like Palomar, with the power of spectroscopy, and with the realization that galaxies were not part of the Milky Way, these fuzzy blobs were not part of the Milky Way, but in fact, their own island universes out there after the great debate in the early part of the 20th century, one could actually begin to do the history of the universe. And that was accomplished by noticing two critical things. The first is that galaxies, when they move away from us, have that Doppler effect, right? We already mentioned this. We already understand the relative motion. So if this is a spectrum of hydrogen and a couple of other lines down in the bottom, a nearby star that's moving away from us may have a little bit, but a very distant galaxy may have a spectrum which is shifted significantly to the right. Okay, so what? It's not enough to know that something is moving away from you. That galaxy could be very, very close to us, but moving at great speed, or it could be very far away from us and moving at great speed, and it would give you the same shift. You still need to know the distance to that galaxy. And I have a whole other talk, which I could give some time on how we discover distances, but I'll make a very brief version of why that's important here. And that's this woman, Henrietta Swan Leavitt. Henrietta Swan Leavitt was hired in 1895 as a computer at Harvard. In a laboratory at Harvard, a number of women who were extremely powerful astronomers were set down to do computational grunt work because the men in the office didn't want to sully themselves with spending all that time doing calculations and writing down catalogs and whatnot. But Henrietta Swan Leavitt realized something, that there was a direct relationship between the period, the amount of time, and the brightness, aka the luminosity, of a pulsation of a specific type of star called a Cepheid variable. And if you know the absolute brightness of something, the true brightness of something, you can get its distance. Think about a light bulb, a 100-watt light bulb. A 100-watt light bulb is a 100-watt light bulb no matter how far away it is from you. But if you put a 100-watt light bulb right in front of your face, and then if you put it 100 meters away, it looks much fainter. But if you know it's 100 watts, you can predict its distance based off of how bright it appears. And what Henrietta Swan-Leavitt had done is find a class of star that she knew the exact brightness of if she could measure the period of its pulsation. So what do? You go to a telescope like Palomar, you look at galaxies, you look for these pulsating stars. You can figure out their brightness, their true brightness, based off of Swan-Leavitt's relationship. Then you use the redshift of the galaxy to determine their distance. And this guy, Edwin Hubble, did that and came up with a series of observations that were critically important. That galaxies, on average, the farther they are away from us, the faster they're moving away from us. Now, why is that important? Because if you run the clock backwards, that predicts a beginning to the universe.
Generating energy diffusion as it radiates away.
Oh, I think there's an open mic somewhere. Thank you. And this is Hubble's great figure, the velocity distance relation amongst extragalactic nebulae, aka galaxies. The farther away they are, the faster they're moving away from us. And if you take the slope of this, you get what's called the Hubble constant. And that allows you to predict a start to the universe, which we now call the Big Bang. This is highly controversial at the time, and in some ways remains controversial. But this now set a starting point for the universe that was certainly not static and certainly not eternal. This was the birth of modern cosmology, and it all goes back to a woman who was relegated as a calculator in an office. Number 3, the trivial question of the composition of the universe. It is a fair assumption, and in fact, it was the primary assumption for most of time that we understood atoms, that the universe was made purely of atoms and light, right? So in a simple model of the universe, here is the pie chart of the composition of the universe. It's all atoms. Well, a woman named Vera Rubin, using a variety of telescopes, taking spectra of stars in the outskirts of galaxies and measuring the speed at which they were going around those galaxies, realized something. What she realized was that compared to what they should be doing, stars were going around their galaxies much faster than they should if they were just orbiting around all the mass on the inside of the galaxy, and all the mass was made out of atoms in the form of stars and gas. That's summarized as an example here in this figure on the right. The dotted line is what it should be if there's only atoms inside that galaxy. And what Vera Rubin observed using spectroscopy was that there's significantly more stuff in those galaxies. For the stars to be moving that fast, that far out from the galaxy, there had to be about a factor of 10 more stuff in there. And it is the first rule of astronomers that if you don't know what something is, you call it dark. And this was the slam dunk verification of an idea that Fritz Zwicky and others had come up with earlier for dark matter. Rubin's measurements proved the concept of dark matter. But what Rubin's observations couldn't do was tell you about the relative amounts. Was there a lot of dark matter and only a few atoms? That's what the galaxies seemed to indicate. It was about a factor of 10 more dark matter than atoms in some galaxies. But we had to go farther. Here is a star called a white dwarf. It's what our sun will eventually be. It's sitting there on the right. And it has a rather pesky neighbor who is close enough that gravitationally the outer parts of that star are falling on to the white dwarf. This is a whole nother talk, but it's a cardinal rule of white dwarfs that you cannot have more than 1.4 solar masses of stuff on them. Otherwise, the white dwarf explodes. Okay, what does that have to do with anything? What that has to do with anything is the fact that I said 1.4 solar masses. That means I know exactly how much stuff is in the white dwarf when it explodes. But if I know exactly how much stuff is in the white dwarf when it explodes, I know exactly how much energy it has. And once again, like the 100-watt light bulb, if I know exactly how much energy there is in there, I know its brightness. It's now just a function of how far away it is to see what its distance is. This is what's known as a type 1a supernova. And here's the spectrum of those things. Type 1a supernovae look very odd. They've got these huge, broad absorption features. But the critical thing is that they have these predictive lines. And because of the predictive lines and the redshift, I can now figure out the distances to them. And that's what was done in the early to mid 1990s. And Hubble's prediction of where the universe should be is that bottom dark line. But you'll notice that all those red dots for objects which are extremely far away are above Hubble's line, which means they are farther away than we expect them to be. And if they're farther away than we expect it to be, we expect them to be, then that means not only is the universe expanding as in Hubble's model, but that expansion is speeding up by some unknown contribution. And remember, first rule of cosmology is if you don't know what something is, you name it dark. This was the discovery of dark energy. But again, we don't know the relative amounts of these things. Now, many years have gone by. And one of the things that I did in my doctoral thesis, and Stephen mentioned this, is that I have an interest in Big Bang nucleosynthesis. In the Big Bang model of cosmology, the universe was very, very hot early on. So hot, in fact, that protons and neutrons were moving around too quickly to even fuse and join up and make simple nuclei. But as the universe expanded, it cooled down. And at about 2.5 minutes after the bang, the first heavy nuclei were formed: helium, a little bit of lithium, and an isotope of hydrogen called deuterium. Now, it's far too much time for me to explain all the processes involved here. But one thing that I can tell you is that the amount of deuterium produced in this process is an extremely sensitive function of how many atoms there are in the universe. If there are too many protons or too many neutrons, you make different amounts of deuterium, either too high or too low. And the fun thing about deuterium is that it was created only in the Big Bang, only in the Big Bang, unlike all the other elements in the periodic table. So if you could ever find a place in the universe where you could measure deuterium, and you believed that it hasn't been inside of a star because deuterium's fragile, gets destroyed very easily by stars, then you could measure by proxy the total number of atoms in the universe. This is the process of Big Bang nucleosynthesis. It predicts as a function of how many elements, of how many atoms, excuse me, there are in the universe, the relative amounts of these things. The key one is that orange line, which is an extremely sensitive function of the total atomic density of the universe. And if you have a very good spectrograph and a very patient set of observers, you can measure that deuterium line. That's what's in the center of this figure, that little dip down. Those are the Balmer lines, or sorry, the Lyman lines of deuterium. And it's in a gas cloud about 12 billion light years away, a gas cloud that's never been inside of a star, measured by a spectrograph here on Earth on the summit of Mauna Kea. And these measurements were made in the late 1990s, and they provided definitive proof that the relative amount of atoms in the universe is only about 5%. So 95% of the universe is in a form of matter we don't understand, or energy. Everything that we know, atoms and light, only constitutes 5% of the energy density of the universe. And each aspects of this pie chart are only possible because of spectroscopy and looking farther and further out. The last one that I'll mention is the downright boring subject of whether or not we're alone in the universe. Remember that Doppler shift. If it's moving away from you, it's redshift. If it's moving towards you, it's blue shifted. Well, if I were to take the spectrum of a star and watch it very, very carefully, sometimes I might see it do this. Wobble left and right, red shift, then blue shift, red shift, then blue shift. Why is it doing that? It's because it's orbiting the barycenter, the center of mass, of a star-planet system. gravity rules, right? Right now, the center of the sun is not the center of the solar system. The sun is actually moving at around 10 centimeters per second around the center of the entire center of mass of the solar system. And this technique was used in the early 1990s to discover thousands of planets around other stars. We call this the radial velocity method. All those green dots are measurements simply of the spectrum of the star, inferring the presence of an unseen planetary companion. The planetary companion is unseen because the star is 10 billion times brighter than the planet, so they are very hard to see. But this technique offers one of the critical ways to figure out if there are planets like our own, orbiting stars like our sun, out there in the galaxy, and presumably, because the laws of physics are the same everywhere, out there in the universe. And so this is going to be one of the key techniques that we do to go after those stars which have about an Earth mass orbiting around 1 AU from their parent stars. It's not the only technique, but it's the best technique to determine the mass of those planets. Whenever you hear in the popular media, oh, hey, Earth-like planet found, the first question you should ask is, what is its mass? And if they don't have an answer for that, it's not Earth-like. You need a technique like this to determine its mass. So those are four highlights, I think, of the last 120 years for spectroscopy. And many of those measurements, in fact, aspects of all of those measurements have been happening at Keck. I have to brag on my observatory a little bit. Although I should point out that Keck and Palomar have been very good partners for quite a long time. In fact, Stephen mentioned the PARVI instrument having engineering work happening this week. PARVI is the baseline instrument that we are using to understand the technology for an instrument which we call high spec, which will be coming to Keck in a couple of years. So Palomar and Keck work very closely together with our Caltech partners to help develop instrumentation to eventually come to Keck. The key power of Keck over its last 25, 30 years has been spectrographs, right? This is data and images of the many spectrographs we have on Keck. We have about 8 spectrographs on Keck. It is our bread and butter. Spectroscopy is our powerhouse. It's what we use to determine all the things that we do. We do very little imaging at Keck right now. It's almost entirely spectroscopy. We do infrared spectroscopy. We do optical spectroscopy. We sometimes do spectroscopy in the near ultraviolet, around 3,000 angstroms right before the Earth's atmosphere cuts it off. We do it at very high resolution, at very low resolution. And we basically go over the entire visible lifetime of the universe, or most of it, with our spectrographs. And now I want to close with what I think the next frontier is for spectroscopy. The first is the universe in 3D. With an instrument that was developed at Palomar called CWI, the Cosmic Web Imager, developed at Palomar and then upgraded to what we call the KCWI, the Keck Cosmic Web Imager, we are now able to take an image. Well, this is a Hubble image, so it's particularly nice. But here is that image through KCWI. And you can say, well, I thought you wanted to do spectra. Well, the wonderful thing about this image is that every one of those pixels is actually a spectrum. So what you see here is if I rotate that image and look in wavelength space, so wavelength is left to right now, and you see those little blurps inside of there. Those are clouds of gas inside of a galaxy radiating around specific wavelengths for oxygen. These are special lines of oxygen in that galaxy. But now we can do it throughout the entire galaxy. So this is that same thing, but now over a much larger wavelength space. You can see multiple absorption features, multiple emission features. If you're careful, you'll notice that some of these notches that are bright are also matching absorption features in the arms of the galaxy. So this is a key capability. Instead of looking at only one tiny part of a galaxy, we can now look at the whole galaxy at once and get spectra all across that galaxy. Huge power increase in our understanding of galaxies. We're always going for the farthest and the faintest. This is one of the most distant galaxies ever to be observed in terms of getting its spectrum. At a redshift of 7.5, I won't even go into redshifts. The key thing is that the light left that object about 13 billion years ago, most of the age of the universe years ago. These spectra of these galaxies now take light, which was normally in the far ultraviolet, and redshift it way out into the infrared. And Keck is pioneering ways to use infrared spectrographs to go after these things. We go after fast radio bursts. So this is multi-messenger astronomy, going after things which are found sometimes in radio or even neutrinos or gravitational waves and following them up. And then the one that's really going to change everything, I think, and probably is going to do so in the next 20 to 25 years, is our ability to turn off those stars through a process of coronagraphy and obtain the spectra of the planets orbiting around them. So what's shown here is a simulation of what our solar system would look like with a 10-meter telescope out in space, staring back at the solar system if it was 30 light years away. And this is an extremely hard measurement to do. But if you can manage to get a spectrum of that blue dot at about 2 o'clock on the diagram, you would get this. The green spectrum is the spectrum of the Earth. And the fun thing about that is that that spectrum has water, methane, ozone, oxygen, carbon dioxide, and it has them in very specific ratios. Those specific ratios only occur if there's life on that planet. So with the tools of spectroscopy, the power of very large telescopes, we may be able to actually determine whether or not other planets have life on them. And that's probably one of the most profound things that we could possibly do. So let's go back to our image of nothing. One of the things that Keck did after the Hubble Deep Field was to take a spectrograph and try to get a spectrum of as many galaxies as possible in this image. Spent quite a while doing it and got the redshifts of those galaxies, distances to them, assuming a cosmology. And so what's fun about this, and I really hope it works online because of internet speeds, but because we now know the distances to these galaxies, we have the full context. We know what they're made out of. We know what their temperatures are. We know how old they are. We know how distant they are. So what we can do is actually fly through that image. Some of the small things are actually quite close by. Some of the small things are at moderate distance, right? Most of the large things are fairly close. And this is not just a CGI thing. This is taking those images and then stacking them as a function of distance and flying away. But most of those tiny little dots in that image are actually galaxies that are exceedingly far away. Some of them more than 10 billion light years distance. And in my mind, that's why nothing can be wonderful. So with that, I think I'll stop and happily take some questions.
Dr. O'Mara, thank you very much. Thank you very much. You can turn on microphones and really the floor is open. Floor is open for questions. Well, let me see if I can warm the crowd up a little bit. What's the difference between a diffraction grating and a grism?
Oh, they're very similar. So a grating can be a reflective thing. For example, you can look for the light bouncing off of it, or you can have a transmissive grating. A grism is a grating prism. It's a combination of a grating and a prism. And so you'll do a grating kind of right on the prism. But it's the grism is just a grating prism. They're all the same principle. They're all just a way to etch fine lines onto glass to get much higher resolution. But it's basically a dispersive element. They're both dispersive elements.
Okay.
Bob asks, when you say low resolution at Keck, what R value is that? We can go as low as, so that's that spectrum of a planet, that's down to R of 70, very, very low. So we go from R in the hundreds in general to our highest resolution spectrographs are R of about 100,000. So we go anywhere between 100 and 100,000, not all in the same instrument. It just depends on what we're trying to do. For very, very faint objects, we go to lower resolution just because we want to get as much light down the bucket as possible. But for very bright objects, or if you're very patient, we use the high resolution to really go after the atomic structure and very fine detail in the lines.
And what is that R value measuring?
Oh, that R value just tells you your ability to separate two spectroscopic features. So it's basically the delta lambda, the change in wavelength over lambda, tells you how well you can measure two objects. So if a good example is if you take your fingers at arm length and put your two fingers up, you can easily see that they're well separated. If you have somebody stand across a football field and hold two fingers just kind of straight up, it's very difficult to see that those two things are separated. And that's because the resolution of your eye, the R value of your eye, can only measure a certain level of precision. So a very large R number means a very small wavelength separation is possible to see. Norman says, you talked about helium and the abundance of atoms in the universe. How does antimatter feature into this estimate? Excellent question. To the best of our knowledge, almost all of the antimatter in the universe was destroyed by matter in the universe extremely early in the history of the universe, well before those few 3 minutes. So any protons and antiprotons went and created light. Same with electrons and positrons. So there's very little antimatter out there in the universe right now. Let's see, I don't know who's got the background there. But it, sorry.
All right, sorry about that. Not sure where that's coming from.
Coming from Hugh.
You?
Okay, I think we've got it. No? All right.
Okay.
So Norman, about how does antimatter feature into the estimate? So right now, the amount of antimatter in the universe, except for stuff that's made in very, very high energy places, is exceedingly small, triflingly small, so that its contribution to the mass energy of amount of the universe is a fraction of a fraction of a fraction. It's very important in understanding how things happen in highly energetic environments, and it's critical to what happens in nuclear events in the centers of stars. But it's basically produced in very high energy environments and then almost immediately destroyed. So the positrons that are created in the sun almost immediately combine with electrons and make gamma rays. So in terms of the total mass energy budget, it's very small.
Thank you. I was just wondering how the, obviously in the initial stages, concentration would be extremely high. Therefore, your annihilation would occur at very high efficiency. But obviously, as they dilute, the efficiency, that reaction rate drops off.
Yeah, they were in the early parts of the universe where there was basically one part, and I forget the amount difference. For every positron, there was a proton plus 1/10,000,000th of a proton. So it was only the protons that remained, because the protons and the antiprotons of the electrons and the positrons, they all annihilated in the very, very early parts. They were produced because it was extremely high temperature and then immediately annihilated and made light. So, Aviana asks, how big is the link between Keck and CERN? Not very strong. CERN helps create environments similar to those very early in the Big Bang to test the nuclear physics reactions themselves. But we don't have an explicit link in terms of shared research projects or things like that. So it's more of an indirect partnership of understanding nuclear processes and things like that.
I have a question.
Yeah.
They always say the key to spectroscopy is knowing where to put the slit. If you're taking a spectrum of a galaxy,
Mhm.
now you could conceivably sweep that slit across different parts of the galaxy and maybe get different results.
Yes.
How does that work?
Well, in fact, I'll go back to this slide. So let's say I've got this galaxy in the lower right-hand side. And I were to put a slit left to right across the center of that galaxy, the brightest part there. And then I were to move a slit up to one of those spiral arms and put a slit across it. The spectra of those two things would be very, very different. And the reason is the types of stars and gas in the bulge of that galaxy, the center part, are an older mixture of population of stars than the stuff out in the arms, which are typically a younger population and brighter in that oxygen line because they're actively forming stars. So I could take a slit and just step down across that galaxy. But the reason why we built this instrument is so that I can do it all at once. Instead of waiting that amount of time to take that spectrum, move down, spectrum, move down, spectrum, move down, spectrum. That's a very tedious process. Most of the time when they say where to put the slit, it's for galaxies which are so distant that you get almost the entire galaxy in the slit at once. And that's usually you're trying to get the distance to that galaxy, and not a whole lot more is gleanable, except for the bulk properties of the gas and inside of that galaxy, instead of something like this, which was for a nearby galaxy where you can easily see those clouds of oxygen atoms inside of it. And that's really only possible to get the 3D structure of those clouds by stepping the slit all the way down, or by using this type of spectrograph, which is called an integral field unit, which does it all at once. The integral field spectroscopy, you can say, well, why didn't they do that at the beginning? The answer is that they're extremely hard to build. Very, very delicate optics, and very, very hard to reconstruct the data. John, can you speak to the possible, this is from Lee Courtney. John, can you speak to the possible contributions and challenges of spectroscopy in the amateur community, both observing and offline with data sets from the professional community? I think one of the really exciting things that the amateur community can do is look at stars every night for which they're bright enough to get fairly decent spectra. Because a good example of this is Betelgeuse, right? Betelgeuse had this period of time where it was dimming, and we didn't know what the heck was going on. Now, if I were to take Keck and point it at Betelgeuse right now, I'd get in a lot of trouble because it's too dang bright, right? So instead, ideally, what you would like to do is have a good spectrograph constantly looking at stars like Betelgeuse. And that's a really powerful thing that the amateur community can do. Because if we have constant monitoring of stars in the sky and look for differences in their spectra over time, that tells you something about the processes in the atmosphere of those stars. So I think that's one of the things that the amateur community could definitely do, and they do. And there's the American Association of Variable Star Observers. That's a combination of amateurs and professionals. But I think spectroscopy of those things is very powerful. Spectroscopy of comets is always very exciting because every comet is unique. So those are two of the things that I can think. The challenges, of course, is that most amateurs live where people live, and the sky is bright. And so the big challenge is subtracting off the spectrum of the night sky, which is oftentimes much, much brighter than the spectrum of the object itself. Jim Nordhausen says James Webb Space Telescope will be a game changer. I 100% agree. I cannot wait to see it launched. It's going to be great. It's going to be a fantastic counterpart to Hubble and to many telescopes on the ground. Thank you, Bob Fosbury, for the kind words. I know Marshall. Yeah. Suggested readings or videos on this topic for deeper understanding. Leah, I think basically, so for example, if you'd like to know about the early universe stuff, the Big Bang nucleosynthesis, there's a book called The First 3 Minutes by Weinberg, which is a really nice tour through this. There's a book called Cosmos, not the Carl Sagan one, but Cosmos, which is a sort of a large history of astronomy, basically from the Middle Ages up until present, but charts the development of spectroscopy very well. Oh, I'm sorry, I missed the question about the iodine sieve. Yeah, I know it as an iodine cell. The question is, what is an iodine cell? This is used in the spectroscopy of exoplanets to try to get that radial velocity. It's used as a technique to make the precision of the wavelength measurement very, very large, because we know where all the absorption lines from iodine should be. So if you pass starlight through iodine gas, you can look at the relative shift against those lines and not depend so much on the wavelength fidelity of your spectrograph.
Other questions? Excuse me.
So one of the challenges for amateurs doing spectroscopy is that spectroscopes that are sold to amateurs are so damned expensive. They're the same cost as the telescope itself. Where can we get a reasonably priced spectroscope to do that?
You're going to love this answer. You can make one. You can actually make a pretty good one. And it can be as simple as, you know, a decent, by decent, I mean a $50 transmission grating and a digital camera. And there's, you know what I'll do is I cannot remember the name, the person who wrote it, but back in the day was that when I was a professor in a college, I did this in my physics lab, which is to create spectrographs. Basically, you need just a couple of simple mirrors, a grating, and a detector, but the detector can be a digital camera of any kind. The trick is not getting the spectrum. The trick is knowing the wavelengths really well. So to do that, you will need to point it at a source like a hydrogen lamp or something like that to get the wavelengths real well. But I can send Stephen the paper that I know of how to build basically your own backyard spectrograph, and it's not bad. It's pretty good, and I can guarantee you it'll cost less than a nice telescope. So
Maybe this could be a project for the Palomar docents, you know, for people like Kin and Curtis, who are sort of expert imagers, and could put together something like this.
You know, you have a good point, because guys in our club who do amateur spectroscopy, and again, they're not many, they buy these Lisa spectrographs, and they have a reasonable R value, but they're like $4,000, $6,000.
oh, I think you can spend far less than that now. There are good, I think it may be from Archon. There are fairly good spectrographs that basically what you do is you run a fiber optic off of, so if you replace the eyepiece with a fiber link, it'll dump it right into a spectrograph for about $200, $300 for the spectrograph, and you can get a really good spectrum off of it.
That sounds, please do send us the material, because there is the little R spec that's basically a filter size diffraction grating, but they aren't terribly accurate, enough to demonstrate the concept.
Yeah, but you can, you shouldn't have to spend thousands of dollars to have fun with spectroscopy. You shouldn't have to. I think there's many different ways you can do it, but it's like with all things telescopes, it's much more fun if you build it yourself. It may not be perfect, but it's kind of fun to play with it and to learn the principles of how the thing works by messing it up first and then getting it right.
Well,
Boy, is this a bunch of nerds talking about fun with spectroscopy?
Hey, nerd pride. There are several 3D printed spec projects on the web. Yep. I think if you, I will do some resource hunting and pass it on to Stephen for you. And it is correct, Sethan, that Vera Rubin did not believe that it was an absolute given. In fact, today, people are not 100% convinced that dark matter is an absolute given. There might be other explanations, but most of the explanations, especially since Rubin's time, are falling by the wayside. But we still don't know exactly what it is.
Speaking,
just wanted to add, I have a friend who does backyard spectroscopy. He's got his own roll-off roof observatory with a C8 and an Alfie on it, and he has a program of monitoring a couple dozen stars as often as it's clear in New Jersey. And like you said, subtracting the background atmospheric is the biggest problem he has.
Yep. Okay.
and speaking, if I could, spending thousands of dollars, here at Palomar, the double spectrograph has been in use for decades.
Mhm.
And finally, we're working to replace it. It has been the workhorse at the observatory. We're working to replace it. There's a project going on that will create an AO-fed non-diffraction limited instrument to be called the next generation Palomar spectrograph. As I understand it, if I read things properly, there's a similar project underway at Keck, and it's a thing called LIGAR. Did I get that right?
Yeah, LIGAR is one of these integral field unit spectrographs, but it's in infrared, and it is behind AO, so that means it is diffraction limited. So it will produce ultra precise images and spectroscopy of a variety of different objects. It's a capability we hope to bring in the next sort of 5 to 10 years.
Yeah, ours will be in development for probably that nearly that long. Other things, other questions?
I'm happy to take one more, and then I have to pop off.
You need to move along.
Yeah, I'm sorry. For those who joined late, I'm actually on vacation right now, and I'm going to get in trouble with my family. So
One more question. Anybody going once? Going twice? With that,
well, well, thank you, everybody. Thank you for the questions. And one thing I can advertise is if you go to keckobservatory.org, we also have a series of presentations. We do about one a month, completely open to the public. We're streaming them live. And so we stream them live and then have a YouTube channel where they're all archived. So if you'd like to go to keckobservatory.org, I think if you just go up to cosmic videos, you should be able to find all those things. Lots of great talks.
and with that, there are no other questions or comments. Let me thank Dr. O'Mara. Thank you for your presentation. Thank you for taking time to speak to us. We greatly appreciate it.
Sure thing.
Let me conclude with a few words about our next speaker. In 2 weeks, May 8th, Dr. Alan Hirschfeld, professor of physics at UMass Dartmouth, will give a talk titled Starlight Detectives: How Astronomers, Inventors, and Eccentrics Discovered the Modern Universe. Dr. Hirschfeld will also discuss his latest book, Introduction to Stars and Planets, an activities-based exploration. Well, again, thank you to Dr. O'Mara, and thank you everybody for attending and supporting the Greenway Talks online. Greatly appreciate it. And with that, goodbye, thank you, and we'll see you in 2 weeks. I'm going to end the meeting with that. Thank you much. Bye-bye.
Thank you, everyone.